Okay, so the goal somehow is to give some lecture with Damian about the following paper by Yamanoi. So proves Pseudo Kobayashi hyperbolicity of subvarieties of general type on Abelian variety. So it's quite a technical paper with many developed tools. And so I will try to extract the idea and main tools. And I think probably the best way is to start a bit with some of the history of former results. So first of all, there is this pseudo-hyperbolicity notion. So I will come back to that first, because it's a bit subtle. So we've seen last week several statements about hyperbolicity, and probably also pseudo-hyperbolicity, but probably not in the sense of Kobayashi. So X is any complex variety. And you consider delta a closed subset. And now you can define pseudo-hyperbolicity. So in all the sense of hyperbolicity you would like. So yes. No, there is key. So X is said to be pseudo Kobayashi hyperbolic if you can find such a delta which will be different from X, such that so there is a proper closed subset, such that if you pick any 2 points in X, then the Kobayashi distance between these points is 0, only in the case where, possibly in the case where both points are in delta. Okay. So this is the Kobayashi pseudo distance. Okay, and so if such a thing is satisfied, we say that X is a Kobayashi hyperbolic modulo delta. And so you can define the same thing for Brody hyperbolicity. So X is a pseudo Brody hyperbolic if same thing, you can find a proper algebraic subset delta such that if you take any entire curve, so non-constant holomorphic map from C to X, then the image of F has to lie inside delta. Okay, so this is the notion of pseudo-hyperbolicity. And in fact, from the point of view of birational geometry, this is the good notion. We saw an example, and we'll see this example appearing again when you take a blow up of hyperbolic variety. It is not hyperbolic anymore, but it is pseudo-hyperbolic. So this is why these are the good notions for Green-Griffiths-Lang conjecture. So, which can be summarized, so X, let's say a complex projective, then X general type, if and only if X is pseudo Kobayashi hyperbolic, if and only if X is pseudo Brody hyperbolic. So this is the way you can phrase Green-Griffiths-Lang conjecture. So, okay. Now I will today focus on maybe and explain some of the importance of Yamanoi. The result is that these two notions are not known to be equivalent. Of course, there is one direction which is true. So if you have something which is a pseudo Kobayashi hyperbolic, it is not difficult to see that it is a pseudo Brody hyperbolic. And in fact, one of the main, or the striking part of the result of Yamanoi is due to the fact that this is not known. I will come back to this point in more details, but it's a bit striking because if you recall Brody characterization, is that if you take X complex compact, there the important point is pseudo, because if you take X complex compact, it is known that Brody hyperbolicity implies Kobayashi hyperbolic. So this is the famous criterion of Brody in the case of compact varieties. But in the pseudo case, so when there is some delta, this is not known. And in fact, Yamanoi will prove something even stronger. So Damian will come back in details, but I already introduced this notion. In fact, Yamanoi will prove that the varieties he's studying, subvarieties of general type in Abelian varieties, are taught, so-called taught modulo delta. So this is again another notion of hyperbolicity. So I recall the definition. I will not go into detail. I think, Damian, you plan to detail this. So if for each sequence of holomorphic map from the disk, so you pick a sequence in the space of holomorphic map from the unit disk to X. So this is a unit disk. If for each sequence, one of the following is true. So you have either that the sequence converges uniformly locally. So Fn has a subsequence which converges locally uniformly. To some F. Holomorphic map from unit disk to X, or you have that for any compact K in the unit disk, and any compact in the complement, then there exist integers such that you have empty intersection between image of K by Fn and N. So this is the so-called notion of tauteness. And this is why Yamanoi will in fact prove. And this is good because, as Damian will explain us, then tauteness modulo delta will imply Kobayashi hyperbolicity modulo delta. Hyperbolic modulo delta. So I think this is an old statement by Kiernan and Kobayashi. The first condition, no. Exactly, yeah. So you have one of these which is happening. So we remark as I said that it was not known if pseudo-Brody hyperbolic was implying Pseudo Kobayashi, and in fact also here one can observe that X taut modulo delta X, that the converse of this is false. So X Kobayashi hyperbolic modulo delta does not imply X taut modulo delta. So I give you the example because it's always the same kind of example. So it's the same example that shows you that Kobayashi hyperbolicity is not a birational notion. So again, you pick up X Kobayashi hyperbolic of dimension at least 2. And you pick a point and you blow up. So the blow up at P. And then delta will just be the exceptional divisor. Then it's easy to see that this is a Kobayashi hyperbolic modulo delta. But this is not taught modulo delta. And it's not difficult to see. So if you pick a local coordinate, around P, and you consider the following sequence of map. So just the following one. Then, well, you see that on X, of course, this sequence locally converges. Yes? Fn of Z, Fn of Z is Z and 1 over 2M. C? Yeah. Okay, so it's a map from the disk to X. And I just take that in local coordinates. So of course, this map converges locally uniformly to F of Z equal to Z. But the lifting, so you can lift the map to the blow-up. This will not be convergent. So let lifting. Then, if you write in local charts the lifting to the blow-up, it's easy to see that the derivative goes to infinity. And this essentially is the proof that it's not tone modulo delta. And then we had a discussion with Benoit. And I think it's also about example, non-compact example, which are Brody hyperbolic. And but not Kobayashi hyperbolic. I think exactly the same proof, in fact, gives you what you said, is that if you consider 3 points over the exceptional divisor, which I've denoted delta, right? Then, if you remove this is Brody hyperbolic. Easy to see because if you take an entire curve, then if you compose it with the blow up, then it has to be constant, right? Because it's Kobayashi hyperbolic. So it means that you have to lie inside the exceptional. But then you avoid. Yeah, exactly. And then you have to lie in this exceptional divisor, which is a P1. You avoid 3 points, so it's constant. But it is not Kobayashi hyperbolic. And the reason is exactly this, is that if you take 2 points on the exceptional, the Kobayashi distance will be 0, in fact, because of this large disk. And there is also another, in fact, proof is maybe easier, in fact, is that when you remove a codimension to subset, the Kobayashi distance doesn't change. It's just the restriction. So it tells you that if you pick any 2 other points, Q1, Q2, different from the PI, and still on delta, then the Kobayashi has to be 0. It has to be 0 because it's 0 for the X tilde, right? So there are several proofs. And I don't remember seeing this example in the literature. Yes. Is it? In Kobayashi, it's in C2.
Yeah, but it's basically what you does here.
Yeah. Yeah. I understand that philosophically it's exactly the same thing, but it's not compact, right? The example of Kobayashi. And it's exactly the same idea, is that on this central disk, you have larger and larger disks as close. So it's the same idea, but it's an interesting consequence that you build something like that. And it's when we discussed with Benoit, he came out with this idea, and indeed it's also what Yamanoi give as example in the introduction. Okay, so this was like a introduction and some side remarks. So now I go to subvarieties of Abelian varieties. Okay, so this Green-Griffiths-Lang conjecture is essentially open, but there is a nice setting where we can obtain many results. It's this setting. So A will be Abelian varieties. And X algebraic subvariety. And so the locus, which will, of course, appear everywhere, is this delta. In this case, it's kind of easy. So this is the so-called special locus. So what can make Abelian subvariety not hyperbolic? Well, if it contains subtori, right, or translated subtori. So this is a natural notion to define the special locus. To say that these are the points in X such that there exists Abelian subvariety of positive dimension. Such that the translated subtori is still in X. Okay, this is the.
So when you say sum,
No, not necessarily. And so, first of all, the birational geometry of this is well understood. So this goes back to odd result of Ueno and Kawamata. So we'll just mention what will be used here. So there is a nice description of subvarieties of general type. So X will be of general type if and only if the special locus of X is different from X. So this is a statement due to Kawamata Ueno. And of course, there is an obvious remark, is that if X is hyperbolic, then its special locus has to be empty, right? So the theorem of Yamanoi, which we plan to explain, is that X is Kobayashi hyperbolic modulo its special locus. This is the main statement of this paper. So I will, I think, yes? Yes.
Especially this in algebraic.
Yes.
Only with finitely many.
Yes.
This is due to
Kawamata. So, so and to understand why Yamanoi paper is in some sense quite complicated, I will explain you why former proof of kind of similar result do not work. Okay. So I will go back a bit in the history to go towards these statements, because Yamanoi proof is really a refinement of what has been done for this kind of result. So of course, a weaker result is to prove the same statement for Brody hyperbolicity. Okay. So this is, of course, a generalization of the same statement with Brody hyperbolicity. So I will first explain you the proof of this result, and we'll see that the proof is, well, much simpler, and then why the classical proof of this statement does not prove this. So this statement is a consequence of the famous theorem of Bloch-Oczai. which tells you what is the Zariski closure of an entire curve. So if you have a holomorphic map from C to A, then the Zariski closure is a translate of an Abelian subvarieties. Okay? It's clear that this statement implies this. So maybe before entering proofs, a few corollary of Yamanoi's result, which are kind of striking. Of Yamanoi is that then you have a proof of Green-Greenfield-Lang for subvarieties of Abelian varieties. Okay. So X in A, then we have that X is general type, which by Ueno Kawamata is exactly that the special locus is not X itself. But then by Yamanoi and this statement, we have exactly hyperbolicity modulo proper subset. Okay. So then X is a pseudo Brody hyperbolic. And same for Pseudo Kobayashi. Okay. So this is immediate corollary of, and this is one of the settings where we can prove in this generality Green-Griffiths-Lang. Okay, so now I will explain you some former result. So let's start with a theorem of Green, which is a special case of empty special locus. Okay, this is certainly included in Yamanoi's statement, right? But there is a much easier proof in this case. So let me give you the proof. The proof uses in a fundamental way Brody's criteria, right? So, and goes, so there is one implication trivial, I prove the other one. So suppose X not hyperbolic, then I want to prove that the special loci is not empty, and even without using this general statement. It's much more easy when you use Brody. So by not, here I say not Kobayashi, hyperbolic, right? But by Brody, if it's not Kobayashi hyperbolic, X is compact, you can produce a Brody curve. Right? So what is a Brody curve? There exists G in X, Brody curve. So it means that it has a bounded derivative, okay? But this is very useful here because we will use the fact that A is a complex torus, so we can lift the curve to Cn. So A is a complex torus. So we have this, and G lifts to Cn, right? So so G tilde is represented by this holomorphic function. Now you pick the flat metric on Cn. So the metric comes from so this also will be used in a crucial way by Yamanoi, that we have this metric on the torus. So a Brody curve means that, so the derivative is bounded. So what does it mean? It means that certainly there is a constant C such that this function is bounded, right? Okay? But, okay, so by Liouville, these derivatives are constant. And so these G tilde are linear. And so you immediately obtain that G is a translate of one parameter group. Of the complex one parameter group. And so if you take its closure, it's still a subgroup of the Abelian variety, and then you have obtained a subtorus, right? So its closure is a non-trivial. Is a non-trivial Abelian subgroup. So it's kind of amazing the difference of complexity between Yamanoi statement and Green statement. So you see, in empty special locus, the proof is not that difficult. So this can be proved in half a page, like in Green's paper, and Yamanoi is 40 or 50 pages. So first, it's quite important to understand why this simple proof does not generalize to Yamanoi set. And this goes back to what I said in the introduction, is that in case of a non-empty special loci, we enter the pseudo-hyperbolic world, and everything is much more difficult. So important is that this proof does not generalize, at least with the tools we have now. To non-empty special locus. Because of the following open questions, which is a very simple question, but the answer seems to be very difficult. And I don't know if people even have an idea of what should be the answer, is that, so you see, if you want to do the same proof, so it means that still you have, suppose it is not Pseudo Kobayashi hyperbolic, then you have still the degeneration of the Kobayashi metric. But what would you like? Get the same proof is that you can produce a Brody curve passing through this point, the precise point where it degenerates, right? If you could prove that, the same proof would work. So the main obstruction is that we do not know that if the Kobayashi pseudo-metric degenerates at a point X, does it imply that there is an entire curve, the non-constant holomorphic map, which passes through this point? This is kind of amazing that we do not know this answer. And even so, here, to get a simple proof like in green, you would like even to produce a Brody curve. And this is known to be false by Winkelmann. So this proof really does not generalize if you want to prove Brody curve. A very nice statement of York, Winkelmann, prove that this question is false for Brody curves. And I think is a counterexample are again of the same kind of, you blow up some subvarieties of Abelian. Exactly. Yeah. So it's constructed through blow up. Okay. So we have to do something, either prove this general statement, but this is not what Yamanoi does. He improves the non-proof of classical statements. So I will give you, because his proof is really a refinement of Bloch-Rothschild theorem. So I will give you the proof of Bloch-Rothschild somehow in the spirit of what Yamanoi does. That will already give you a hint of what is his proof. So let's say it's a proof. Let us give a proof of Bloch-Rothschild. Let's say in the spirit of Yamanoi's proof. So, okay, so he will, I don't know if it's really crucial, if it could be done by using other jet spaces, but he's using the Damian jet spaces. So I will also give a proof using the Damian jet spaces. And he's really using the geometry of these spaces. So I will quickly remember everybody, and maybe almost everybody has already heard of this. We've seen this last week, right? But okay, so this is done through an inductive procedure. I recall you. So you start with a pair. So this is a complex variety, and this is a subbundle of the tangent bundle, right? And what you do is that on a pair, you construct a new variety, which is that just the projectivized tangent bundle. So here is projectivization by Latz. So we have okay, a natural map here. And now you have to define a new pair for the induction. So this is is defined by the following procedure that, okay, I will give you the fiber. So a point in X1 is a point in X and a direction. So it's like this. Okay, and now you will keep vector here at this point, which are sent by the differential of pi to vector collinear to V. Okay, so there are many ways to see this alternative way. Benoit explained us an algebraic way to see this as a proj of sections. This is like another way to see that. And so by induction, you define xk and zk. So important exact sequence is that you see that by definition, the differential of pi map this to the tautological line bundle, right? And so here you have the relative. So at each stage, you have such an exact sequence. So you could also define this the same as the inverse image, but the differential of this tautological. Okay. And what is important for us is the following fact. So the idea is that, so maybe I just, okay, what is easy? That of course, the price to pay when you go to jet is that the dimension increases, right? And here it goes like this. So where n is the dimension of X0 and R is the rank of V0. Okay, and the rank of Vk is constant equal to 1. So what is important geometrically is the fact that, so suppose here you start with this pair, xtx, then you have x1, v1. And now you take, let's say, holomorphic map or gem of holomorphic map from the disk to x, then you can lift it. So holomorphic map, let's say non-constant, then you can lift it to any order. Okay, so the idea is that if you want to study map inside X, you will lift them to the jet space and study them here. So okay. So, okay, so we have a projection here. To X, which is X0. And we've seen this sheaf of differential operators, which can be recovered here the invariant version is just direct image shift. So, okay, on this projectivized bundle, you have tautological bundle. So you can just consider this. And you see that this is exactly the sheaf that maybe we'll forget that, but this is the Demae sample version. And a fact that I will use is the following, which you can find in Demae's notes, is that, okay, so you are interested, as we've seen last week, in positivity property of these sheaves. And so you have a relative positivity in the following sense. So this sheaf is relatively big. And you can prove that, in fact, the base loci correspond to singular jets. And in fact, you can see that starting from order 2, it is not relatively ample. So this can be an issue in computation. And so there is a trick to make it relatively ample is to take a twist of the last one by former tautological bundle at each stage. So there is a property like this. So you consider, so I will do an abuse of notation. I will not denote all the pullback by all the projection. And this is a relatively ample. If A1, so if you have this relation with these integers, and AK minus 1. Okay, so this is a fact that will be used. And so I recall you the fundamental statement the vanishing theorem, which you've seen in many talks last week, is that if you find a section so jet differential here, which vanish on the pullback. So A is ample on X. Okay, then for any if jet has to lie in the zero locus of omega in XK. Okay, so this is what we'll use. Okay, so now let's do the proof. So okay, so we take an entire curve in A, and we consider its Zariski closure. And okay, so we want to work in the jet space, so we just use the triviality of the tangent bundle. Is really the crucial fact, in fact, here. So you see immediately that this implies that any jet space is in fact just a product of A times a variety, which I will denote R and K, which is just the fiber in the construction of the May, right? The May's jets. Okay, so now we have the usual diagram. And the crucial player in this game that is really the key tool is to consider here the projection on the second factor. And so you can consider the map tau k, which is the restriction of xk to this. And in all proof of result that I will present, and in Yamanoi, the key point is to understand the property of this map. So, okay, so suppose, and in fact, the key point will be to measure the non-injectivity of the differential of this map. So suppose that this map is generically finite. Then this is very easy to deduce a contradiction because, as I've recalled you, the tautological bundle on R and K is big, right? So I recall you that it's still on the board. This is relatively big. It exactly means that the O1 on R and K is big. So now you pull back by a generically finite map, it's still big. So you obtain that OXK of 1, which is nothing else than the pullback of this, is big. Okay, but okay, so here I should have be more precise. I consider what I've denoted xk here is the Zariski closure of the lift. Okay? So you see that you obtain a contradiction by the vanishing theorem. Okay? Because this is big, but then you can find some jet differential, okay, non-zero, and it has to satisfy the differential equation, so it cannot be Zariski dense. So you obtain a contradiction. Yes? This is the definition. Xk is exactly the Zariski closure, is the definition. Definition. Xk here, it's a bit confusing. I agree with the notation of Green-Griffiths, but here the definition, I consider xk to be the Zariski closure of the lift. Okay? And I study the property of the second projection map restricted to this. Okay? And I say that if it's generically finite, then this contradicts the vanishing theorem. Is it clear? Yes? Yeah? So I'm a bit late. So what do you want? Me to finish the proof or finish it? Yeah? Okay. So, okay. So supposing that there was a k such that is generically finite is absurd. So this means that for every k, this is not the case. Okay. So for every K, a generic fiber of tau K has a positive dimension. Okay, and now the claim is the following, is that from this fact, I will be able to construct a subtori which will live invariant X. Claim the stabilizer of X has positive dimension. And if I prove this, it's very easy to obtain the statement, Bloch-Rothschild, right? So this is the interesting part that Yamanoi will refine in his paper. So, okay, so you can find certainly an X0 such that this fiber is a positive dimensional, right? Okay, so this means that there exists a germ of a non-constant holomorphic map such that gamma k of t is equal to zt lambda. So this lives in the jet space here, and such that the k jet of x0 is equal to z0 lambda. Okay, this is I've just written the definition that the fiber is positive dimensional. Okay, and now we will just use a Noetherian argument. Noetherian argument. So you just consider the following set, such that these are the elements in A, such that this, of course, belongs to the k-jet of X, but also to the k-jet of the translate. Okay? And you see immediately that this has positive dimensionals, okay, because of this gamma k. So you can just take AT equal to Z0 minus ZT. This lives inside. Okay, you can translate by this, and this still lives. But now we have a sequence like this. Okay, and so by Noetherianity, it has to stop, right? So there exists certainly an order such that they become equal. But considering the Taylor expansion of the k-jet, it immediately tells you that for any A in this, then you have that this has to lie here. This is just a Taylor argument. All derivatives are tangent to xk to any order, so the map has to lie inside this. And now you just take the Zariski closure. Okay, this tells you that A plus X is equal to X. So now, as I said, the conclusion is immediate because you just consider the so-called UNO reduction map. So you have two cases. So either this is a point, but then you get what you want. And if it's not a point, then W is known to be of general type by UNO, right? But this gives you a contradiction, because if you apply what I've just proved, you send your Zariski-Duns entire curve into W, this will give a non-trivial stabilizer. Okay, this cannot exist because it's of general type. So this immediately gives you the Bloch-Kochai statement. So next time, I will explain you the proof of Yamanoi, still in the case of empty spatial loci, but without using Brody. And you see that you kind of need all the machinery that Yamanoi, and this will be, you will see exactly the same scheme of proof. But you have to be much finer on the study of Tokay. He really studies precisely what does it mean that there is a point in xk where the differential is not injected. And he relates that to the, and he proves, tell you spoiler, that he proved that then if there is such a point and a vector, then you can construct a one parameter subgroup. This is the key argument. So this is really a nice refinement of the argument I've presented you. Okay, thank you. I'm already over time. Yeah.
But I have the impression that what he uses is a kind of higher order.
Yes. Yes. You mean this Tokay is like generalization of Gauss map? Yeah.
Yes, it's a kind of
order. Yeah, I agree. Yes. Yes.
After the okay, there is fighting.
Yeah, you study both cases. Yeah.
With Ochi, we described that in terms of function field.
In terms of function.
Yeah, that means the pullback of the transcendental base of the functional field of Rn field. You take the pullback over X forms the transcendental base again.
It's a transcendental, yeah.
Then you can compare the function field with the Z difference by polynomial equation.
Yeah, I think it's probably the same, another way to, it's
formulation of Dumai's vanishing. That is, so I think the Dumai's vanishing, the counterpart to the algebraic relation of the function.
Exactly.
Or algebraic function over the logarithmic differential.
Yeah. So you didn't need somehow the Alford-Schwarz lemma.
No.
You just use a transcendental dimension argument.
We don't use Schwarz or original Nevanlinna.
Nevanlinna. Okay, you need. Okay, which is
Primitive.
Yes, but I think it's kind of the same, in fact, because you,
So
the vanishing theorem is essentially Nevanlinna theory also. Yeah. Yeah.